Hello, everyone. It's Sean Dar, that science guy from the Great Lakes Science Center. We've been using space based telescopes to explore the heavens for many, many years now. Perhaps none is more famous than the Hubble Space Telescope. Well, NASA's about to launch a brand new telescope, one that's more powerful and more complex than we've ever had in space before. And we're very, very pleased to have Mr. Paul Geithner from NASA's Goddard Space Flight Center in Maryland, in Greenbelt, Maryland, to join us and tell us more about this exceptional and incredible instrument. Paul, thank you so much for joining us. What can you tell us about this amazing space-based telescope?
Oh, hi. Thanks for having me. Happy to be here. Yeah, I'm thrilled to talk about this new big space telescope. So I put a few slides together, and I'll talk about what's special about it and why it's so great and what it will do. And I'll be happy to answer questions that anybody has. So this is just a picture of what it's going to look like when it's in space right here. So let's start out. So what is a telescope? A telescope is really a tool of exploration. It makes things that are very far away look closer. And it bends light using either lenses like you might find in a magnifying glass, or more commonly these days, it uses curved mirrors to bend light to do this. And scientists use telescopes to study things that are really, really far away. They're so far away that we can't send robots there or go there ourselves. Mars, which is is a planet right next door, it takes 9 months for us to get a rover there to land on it. And it's relatively close by in the grand scheme of things. The fastest spacecraft we have, which flew by Pluto a couple of years ago, it will take tens of thousands of years for it to get to the next nearest star. And even if you could travel at the speed of light, which is the fastest, it's the speed limit of the universe, it's the fastest anything can go, it takes 4 years to get to the closest star. So we're not going to other star systems anytime soon. And that's why telescopes are so great, because they can explore things that are so much farther away than we can send a robot to, or to go there ourselves. Now, most telescopes are on the ground, but like the Hubble Space Telescopes John Dar mentioned, this one's going to be in space too. So why do we do that? I'll talk about that on the next slide. So what makes a good telescope a good telescope? So first of all, size is bigger is better. The bigger a telescope is, the more it can see. If you can kind of think of a telescope as a bucket, like if you put a drinking glass out in your yard versus a pool out in your yard, and when it rains, which one's going to collect more water? Well, the bigger the pool will, right? So if it rains an inch and your pool is 10 yards wide, it's going to catch a whole lot more water than a glass that's only a couple of inches wide. It'll catch an inch of water, but you pour that water out of the pool or pour it out of the glass, there's a lot more water coming out of the pool, even though it's an inch deep. And light is like those raindrops. So the bigger a telescope is, the more light it can collect and the more it can see. And of course, the mirrors and the optics that make up the telescope, if you make them as perfect as you can make them, then you'll make good images, and you'll see clearly. And the steadier the telescope is, the better it's going to be. Or if it's real jittery, you ever look through a pair of binoculars yourself or a telescope, and if you bump it or you move it, or you try to use one while you're riding in a car, or maybe you're on a boat, the images go all over the place. So you want things to be still. And then location, location, location. The air is a problem, right? Air and clouds, they get in the way, and they blur. That when stars twinkle at night, that's a bad thing for astronomers, because that means there's air currents. And so that's why a lot of ground-based telescopes are put on high mountaintops to try to get above the clouds and as much air as possible. But space is even better because we get away from the atmosphere altogether, and you can take really, really good images from space. So a telescope can be very powerful if you can get it into space. And some kinds of light, different from the kind of light we see with our eyes, some of that light doesn't even go through the air. It gets absorbed, or like what this telescope's going to do, it sees light that's mostly longer wavelength than the red light that we see. And it's got to go somewhere where it can, where the atmosphere won't be giving off that kind of light. So get up in space, and it's only going to see the light it wants to see. So those are things that make a telescope good. So what's different about this one? It's going to be the biggest telescope we put in space yet, much bigger than anything we've ever put in light. And as I mentioned, it sees infrared light. So what is that? Well, radio waves are light, and visible light, which is light we see with our eyes, that's light. Microwaves that are that you might heat something up at home with, that's actually light, but you can't see it. But it'll cook your food. Infrared light is actually light that's a little bit, it's right next to visible light, but you feel it as heat. That's the kind of light we want to see with this telescope. And I'll talk more about why it does that in a little bit. So how big is Webb? Remember, size is the most important thing about a telescope. And look how big this thing is. This is a picture of me in a bunny suit. That's to keep everything clean so we don't get the mirrors dirty, in front of the main mirror of the telescope. And I'm a good 15 feet in front of the telescope. So you can see people back here who are right behind it. Each of these pieces of the mirror is almost 5 feet tall. So this is a big telescope. And this is just the main mirror of the telescope. So we're about that same area as a tennis court. And we're almost as tall as a 4-story building. So we're bigger than a school bus, and Hubble's about the same size as a school bus. So bigger's better. Here's another picture. You see all these little people? This was when we tested the telescope in a giant room that we sucked all the air out of, and we tested the telescope to make sure it's going to work. And this just gives you an idea how really big it is. So it can collect a lot of light and see a lot of things. So what are we going to do? Well, you know, one thing that nobody's ever seen, well, the cool thing about science is you can come up with an idea, a hypothesis, right? You might ask a question, well, how does this work? Or why is this the way it is? And so you form a question, and then you go and you make observations. You go and find out what nature tells you. And that's what we're going to do with Webb. We're going to see a part of the universe that no one has ever seen before. The time when the very first stars and the very first galaxies formed. And we don't know how that happened. So we're hoping to see when the lights turned on in the universe with this telescope. And then, well, how do galaxies grow up? The stuff we're made of is organized at the broadest scale of the universe into galaxies. So that's why we care about galaxies, because that's how stuff like us is we're collected into groups of galaxies. And then galaxies are made of stars and planets. So how are those made? We have a lot of ideas of how this is made, and we can see some of that with some new telescopes, but the James Webb Space Telescope we're going to learn a lot about how stars and planets are made. We'll be able to see other planets around other stars, and we'll even be able to see if other planets in other solar systems, what they're like. And we already know there are some planets that are kind of like Earth that are about the same distance from their star where they could have water and conditions like we have here. So maybe life could be there. So we can actually see if the chemicals that we know that are necessary for life on Earth, whether they exist on other planets around other stars. That's pretty exciting. So here, this thing is so big that it won't fit into the nose cone of its rocket. So we had to design this telescope so it's like an origami observatory. We had to design it so it could be folded up very tightly to fit into the nose cone of its rocket. And here you're seeing right after the rocket sends it into space and it's on its way to its orbit, things that are coming out. So this is the big sun shield. It's a kite. And what we do is the telescope part always stays in the shade of this part. So we always point this thing so that the sun is on the bottom here. And then this part, which is the telescope part, will always be in the shade. And this kite, this big tennis court size kite-like umbrella basically is big enough that we can point the telescope in a lot of different directions and still not get the sun shining on it and see a lot of things. And over the course of a few months, we can point to any object anywhere in the sky. So we can see the whole sky with this telescope, which is hard to do if you're on the ground. For example, if your telescope is on a mountain in California, well, you can't see. There's almost half the sky you never can see because the southern sky that you just can't because you're not tilted that way. But if you're in space and you do things right, you can see the whole sky at once with one telescope. You don't need multiple telescopes to do that. So what are some things we're going to see? Well, this is a really pretty picture that came from the Hubble Space Telescope. And this is of a baby galaxy that is orbiting our big galaxy, the Milky Way. And this is where new stars are forming. But see some of these brown things? These are clouds. And these other stars are between us and the cloud. What you don't see is what's inside the clouds. And with our telescope, we'll actually be able to see what's inside those clouds. Visible light doesn't pass through here, but infrared light does. And we'll actually see new stars and new planets forming inside here. This is a really cool picture. Another one from Hubble of a star that exploded about 1,000 years ago. And the Chinese even wrote about it. So this is what it looks like today. And we'll be able to study things like this in even more detail and try to understand the life cycle of stars, which is pretty cool because we actually are made of stardust. We are the only stuff that was around when the universe started was hydrogen and helium. But you know that we're made of carbon and calcium in our bones and phosphorus, and we need oxygen to breathe. And all those things that are heavier than helium are made inside stars. And anything heavier than iron gets made when a star blows up. So all the stuff that we think is really common elements, they don't exist without stars. Stars are the factories of the universe. And when they're stars, they make elements, and when they blow up, they make the really heavy elements, and all those things are important. So we're made of stardust. All of us are. And by studying stars and dead stars and blown up stars, we'll learn a lot about that. And then here's a picture of Mars. We'll actually be able to look at Mars with this new telescope. But we'll see it in a different way than Hubble does, like this picture. So even though we have rovers on Mars, we're going to be able to see a lot of cool things that we can't see with other things right now. And then here's a picture of a really dusty galaxy, a dirty galaxy we'll be able to look at this with this telescope too and see it in a whole different way. And then this is my last picture. So when the Hubble was first made and put into space, we pointed it at the darkest place in the whole sky where we didn't see any stars, any galaxies. We thought nothing was there, and we just stared at it for a couple of weeks, and this is what happened. There are over 3,000 galaxies in this picture. And how big is this picture? This is as big as a grain of sand if you held it in between your fingers and held it at arm's length. That's how small a piece of the sky this is. And it holds thousands and thousands of galaxies. And some of these galaxies, the redder ones, those are actually really, really far away. And there are some in here that we can't see. And Webb will be able to see ones that the very first galaxies. And that will tell us maybe how they were made and how they evolve over time and how they ended up making stuff like us. So finally, this is my last slide. So this new telescope, this James Webb Space Telescope, or Webb we call it, it's the next great space telescope. And it's going to pick up scientifically where Hubble leaves off. And Hubble has done a lot of great things, so you can imagine this is going to be pretty cool. Now, people actually started about building this thing many years ago, and we started spending money on it as a space agency 25 years ago. And we're fine. And we actually had to invent things to make this thing possible. And it's been a really challenging engineering problem to build this thing. And we're actually done. We're just packing it up to send it to its launch pad, and we're gonna launch it into space as early as late November. We've been working on it a long time. And lastly, like Hubble before it, we think Webb should discover amazing things that no one has even imagined yet. You know, some of the greatest discoveries from the Hubble Space Telescope were answers to questions that nobody even thought to ask at the time. And we think Webb will be like Hubble, and that it will do amazing things that we can't even imagine yet. And that's the end of my show. And I would be delighted to answer some questions or chat with you now.
Paul Geithner, that was just absolutely amazing. I loved all of the images that you shared with us and the video that showed the deployment of the vehicle as well. We've got campers that are all over the place. I think we've got 6 classes that are joining us here today. We even have some campers that are at-home campers, and they've tuned in from home, and they've submitted some questions. Here's some of them, if you've got a moment.
Sure.
This one comes from one of our kindergarten campers. They want to know, what does the moon look like through a telescope?
Oh, the moon is one of my favorite things to look at with my own telescope. And the moon is just full of craters and mountains and valleys, and it is fascinating to look at. And if you get a chance to look at it yourself, even with binoculars, it'll blow your mind. It's really neat to look at. And, you know, a good time to look at the moon is not when it's full, but when it's only a little bit lit, like when it's a crescent, because then the shadows are long and you really see the dramatic, the height difference between the mountains and the craters and the valleys really comes out. And it's so bright that if you, it's a good time to look at it too, is when it's only partly full and not a full moon. But yeah, the moon looks really cool with a telescope.
Well, thank you for sharing that. I know that our kindergartners have all seen the moon when they looked up in the nighttime sky, but they really wanted to know what it would look like through a telescope. Here's another question. This question comes from 2 of our students that are in Miss Alicia's class. I believe it's Arnav and Isaiah. They want to know, how is it possible to operate a telescope that's so far away?
Oh, that's a great question. So we actually, we're always in contact with it by radio. So if you think of, like, if you know anybody with a drone, or like a remote controlled airplane or something like that, it's the same thing. We control it with, we send radio signals to it, and and we tell it what to do that way. So and it has its own onboard computer, so it knows where it is and where it's pointing, and it's aware of its surroundings. So and we load up instructions like, look at this planet or look at this star for this long with this camera, and it'll do it. So yep, we talk to it by radio, and we're always in contact with it.
That is so cool. So amazing. It sounds so sophisticated. Here's a question. This one comes from one of our third grade campers that's in Miss Mary's class. And this camper wants to know, are there different kinds of telescopes, and what are they made of?
Oh, great question. Yes, there are many different types of telescopes. So there's no one telescope that can see all kinds of light, right? We have Hubble sees visible light. It also sees ultraviolet light, which is what gives you a sunburn, but you can't see it, right? And it sees a little bit of infrared light, which is the kind of light that Webb is going to see. But there are such things as radio telescopes, big antenna dishes out in the desert that look at radio, and they take pictures of galaxies in what they look like in radio emission, and that's really cool. And then there's even X-ray and gamma ray telescopes, and they look at light that, if you know X-rays are really short wavelengths of light. They're so short that they'll go right through you, and you can take pictures of your bones, right? So X-rays but you have to go to space to do that, because the air will absorb too much of X-rays. Thank goodness, because it protects us, right, on Earth. But there are X-ray and gamma ray telescopes, and those are in space, and they study the most energetic things that happen in the universe, like black holes and neutron stars colliding, and that release more energy than a whole galaxy does over years. They'll emit more energy than that in a split second. And so there are all kinds of different telescopes to see all kinds of different things that nature shows us.
Wow. Man, we're learning so much with you today. Another question for you. This one is from one of our first grade campers. They'd like to know, what was your favorite thing that you've done at NASA?
Oh, that's a good question. One of probably my most favorite thing was I got to work on fixing the Hubble Space Telescope. It had a mirror that was the wrong shape, made to the wrong shape, and we had to basically fit it with glasses. And I worked on those glasses, and that was pretty cool to see it work absolutely perfectly. And that's maybe the most fun. And I've certainly had a good time working on building Webb, because when I started working on Webb, it was just cartoons. It wasn't real. And now we've built this amazing machine that couldn't have existed 20 years ago. And now it's a real thing, and we're about to launch it into space.
You must be so excited. I'm excited just listening to you. Question here. This one is from the students in Miss Sarah's class. Miss Sarah works with our first and second grade campers. They want to know about asteroids and black holes. How are asteroids and black holes made?
Oh, wow. Great question. So asteroids, we think there's a lot of asteroids between Mars and Jupiter in our own solar system. And what we think they are basically rocks that didn't come together and glue themselves together and make a big planet. Mainly because Jupiter is a really big planet with a lot of gravity, and it won't let those rocks pile up into one planet. So, but we think they came from dust that formed the entire solar system. So 4.5 billion years ago, that's when the solar system was born. And there was a lot of really tiny dust, not rocks, but dust that under their own gravity collapsed and made the sun and the planets and the asteroids. So asteroids are really made of the the dust, the dirt that was created from some previous star that died and blew up and made a bunch of elements like I talked about earlier. And then black holes are interesting. We don't know everything. We don't know a lot about a lot of things, but black holes, we do know that really big stars that are bigger than our sun, when they die, they have so much mass that they will collapse into they'll basically collapse. They'll collapse into a black hole, and a black hole is a thing that has so much gravity that light can't even escape from it, and we don't even completely understand the physics of how black holes work. Like, for example, time stops. If you could stand on the surface of a black hole, if it had a surface, time would stand still. It's weird. Things get really weird with black holes. And then in the middle of every big galaxy that we see is a black hole that's millions and millions of times the mass of our own sun. And we don't know how they got there. And we think they're necessary for galaxies to be galaxies. So that's one of the questions we want to answer with Webb is, well, how did those big things form so early in the universe? And, where did they come from and how did they evolve? But black holes are basically humongous super gravity things that were the physics that we understand in our everyday lives. None of that applies.
Wow, that's amazing. We've got so much to learn. I can't wait for the James Webb Telescope to get up there so we can learn more.
Yes.
More questions for you. This one is from Miss MJ's class. She works with our second grade campers. Cameron in that class wants to know how big the moon is.
The moon is, that's a great question. So the moon's smaller than the Earth, but it's pretty big as far as moons in our own solar system go. It's about a quarter the diameter of the Earth, but that means it's only so volume goes with the cube of diameter. So you have to take diameter times diameter times diameter. So a quarter times a quarter times a quarter is, whoa! Now you're down to something that's only got 1/64th the volume of the Earth. So if you look at the Earth and the moon, if you're out in space and could see them both at the same time, you're like, wow, the moon's about a quarter the diameter of the Earth. But as far as how much stuff is in the moon, it's actually a lot less. And in fact, the moon is a little bit lighter than the Earth. So it actually has about 1/81th the mass of the Earth. But it's big as moons go, and relative to its host planet, which is us, Earth, it's actually really big. And the moon we think is really important for how life evolved on Earth. It helps stabilize the tilt of the Earth's axis, so we don't have super extreme seasons. Mars doesn't have a big moon, for example, and it can tilt. The tilt of its axis, which is what causes seasons, can vary by tens of degrees, whereas on Earth it only varies by like less than 2 degrees, and over thousands and thousands of years. And so, and the moon pulls on the Earth to create the tides, right? The ocean tides, and that may have had a lot to do with how life moved, which started in the ocean, got started on land, and ended up with stuff like us. So the moon is, moon's pretty big relative to the Earth, but it's still kind of a lot smaller than the Earth. But it's also a really important thing to our life on Earth.
Wow, I'm looking at my watch. I could go on all day long. I think we've got time for maybe one, maybe two questions at the very most. Here's another question for you. And you mentioned gravity, and some of our kindergarten students want to know, how can there be less gravity in space?
So that's a great question. So mass, this is going to be a little weird, but so things that have mass, things that weigh something, have they create gravity. Gravity is just a property of when you put a lot of stuff together, it pulls things towards them. Well, if you're out in space, if you're orbiting something, it's like you're always falling into it. And so you don't weigh anything, or you're not standing on the surface of something with a lot of mass. So you're weightless. You still have mass, but you don't feel the force of gravity. And things that orbit, like our astronauts that are on the space station, it's orbiting a couple 100 miles over our heads. They're in the gravitational field of the Earth, but they're circling the Earth in like a free fall. So, if you jump off of something like you climb a tree and you jump down, and for a moment you feel your stomach comes up, or you're on a roller coaster and you head down the steep hill, you feel that's weightlessness. You're not feeling the force of gravity on you. And that's, so yeah, you're if you're in space and you're not standing on the surface of something and you're just like orbiting the Earth or the sun, you don't feel the effect of gravity.
Well, Mr. Geithner, I have so many questions, but we only have time for one last question. Okay. And I want to make sure that we get a really good question in here for you. Here's one. This one is from Miss Mary's 3rd grade class, and students in that class want to know, how far away will the Webb telescope be?
Oh, nice question. So we're going to send it about 1 million miles away, which is about 4 times farther away than the moon. So it's going to be, if you look straight up at midnight and go 1 million miles away, that's where we're going to be. And we're going there because we want to get away from the Earth, and we don't want light from the Earth to pollute our observations. And we can stay behind a big umbrella and keep the Earth and the sun on one side of that umbrella and the telescope part on the other, and that way we can see what we want to see.
Wow, that sounds absolutely fascinating. I think that we're just about out of time, but I want to remind everybody who's watching that if you are interested in learning more, you can always visit NASA's website, and I believe that's at www.nasa.gov. There's plenty of great information about the James Webb Telescope that you'll be able to see when you go to that location. Once again, folks, we've been interviewing Mr. Paul Geithner, and he is the Deputy Director of the James Webb Telescope. He's been joining us from all the way from Greenbelt, Maryland, at NASA's Goddard Space Flight Center. Thank you so much for spending time with us. I know that I certainly learned a lot, and I believe that all of our campers at Camp Curiosity learned a great deal as well.
Well, thanks for having me.
Our pleasure. Our pleasure.